My name is Gustavo. I'm from here, from Cantabria. I am studying ecotones in environmental sciences. My future doctoral studies.
Hola, buenos días. Soy Pilar Bueno, soy de Valencia y trabajo en biología como profesora en un instituto.
I'm Enrique. I came from Seville and I'm a PhD student in microbiology.
Hi, I'm Alberto and I'm from here, from Spain, and I'm studying biology degree, and that's all.
Wait. I'm Fernando. I'm from Spain. I'm at the CAP studying gases.
I'm Joana. I'm from Portugal. Right now I'm staying in Centro Astrobiología, and I'm working with catalysts for methane formation in aerothermal vents.
My name is Jen. I come from Texas A&M University. I'm a geologist looking at the early record of life. I do modern experiments growing microbial mats and compare the morphology of modern mats to ancient mats.
My name is Alba. I'm from Spain and I'm working in planetary geology department of Centro Astrobiología.
My name is Javier. I'm an engineer and I'm working also in the Centro Astrobiología.
My name is Sara Carretero. I come from Madrid and I'm also in the Centro Astrobiología of Madrid. That's it.
I'm Marta. I'm from Portugal as well. I'm in my last year of my master's degree, and this year I work on resistance mechanisms to ultraviolet radiation in biology.
I'm María Luisa Martín. I came from Madrid and I'm studying the biodiversity from extreme environments at the Centre for Astrobiology.
I'm Lucia. I'm from Oviedo, and this year I just finished my degree in physics.
I'm Maria. I'm from Oviedo too, and I'm starting my last year of physics in the branch of astrophysics.
I'm Carlos. I came from Oviedo. I'm studying my third year of chemistry degree. There's nothing more to say.
Hello, my name is Jose. I'm from Spain, and I studied biology in the University of Valencia. And this year is my first PhD year, and I am making Corcongados. My work is my job is in Astrobiology Centre, and my work that is geomicrobiology of sediments of Rio of Tinto River.
My name is Cecilia Liam. I'm from the University of Arizona Lunar and Planetary Lab. I work on Mars atmospheres and looking at surface and atmosphere volatile exchange.
My name is Catherine Lanier. I'm a third year biochemistry PhD student at Georgia Tech in Lauren Williams' lab. I am studying the origins of life using the ribosome.
I'm Zach Duke. I'm also at Georgia Tech. I'm a first-year residency, second-year grad student in biochemistry, and similar to George, I do the same thing: microchip capillary electrophoresis combined with laser-induced fluorescence to look for organics in Mars analog, icy moon analog, and other extreme environments.
My name is Barbara Fuente. I'm originally from Spain, but now I'm doing my third year of PhD in the University of Arizona in Tucson. I do crystallography and mineralogy, and also I do databases for mineralogy and astrobiology.
My name is Alyssa, and I'm a third-year PhD student in physics at Arizona State University. And I study the physics of life, meaning physical laws that separate life from non-life.
Hello, I'm David. I'm from Berkeley, California, and I study the interaction between minerals and organic molecules, specifically trying to use UV light to produce, catalyze organic reactions that could have been on the early Earth.
Hello, my name is Alberto. This is my first year of my PhD at the CBM. My research is focusing on unit damage response.
Yo soy Beatriz, soy la periodista infiltrada.
I'm studying chemistry. I'm in degree.
Hello, my name is Rafael. I'm from Spain. I am a biologist. I was doing a collaboration with the Centro Astrobiología at the XIII laboratory, working with acidophiles. And now I'm looking for financial support because I would like to do an PhD.
Hello, my name is Antonio. I come from Valencia. This year I finished the master in geological physics, and I'm here to enjoy this experience.
Hello, my name is Marina. I'm from Madrid and I'm studying my degree in physics.
Hi, I'm Sarah. I'm from Spain, Madrid, and I'm studying my degree in physics.
Hi, I am Gabriel and I am third year studying physics too.
I'm George Cody. I'm at the Carnegie Institution of Washington's Geophysical Laboratory, and I'm a geochemist. Carlos.
Okay, I'm Carlos. I work at the Centro for Astrobiology in Madrid. I studied chemistry some years ago. And I specialized on biochemistry and molecular biology, and now I run a laboratory there focused on different aspects related to the origin of life and RNA walls.
I'm Victoria Meadows. I'm a professor of astronomy at the University of Washington. I'm also the director of the astrobiology program at the University of Washington and the principal investigator of the NASA Astrobiology Institute's British Planetary Laboratory. And my training is in planetary astronomy, but now I am more interested in how we would recognize whether an extrasolar planet could support life or have life.
My name is Cole Mathis, third-year graduate student at Arizona State, and I study sort of abstract models of chemistry to understand what kinds of constraints make life more probable.
Okay, my name is Javier Gómez-Elvira. I am the ex-director of the CAB from 1 month ago. I am engineering, and I work in instrumentation. I am the PI of one of the instruments of the university, the REMS, and we work in instrumentation in the future.
My name is Michael. I'm from California. I'm a PhD student in planetary science at Caltech, and my work has been mainly about modeling photochemistry in planetary atmospheres.
My name is Matt. I'm at the University of Washington, and I primarily focus on Precambrian nitrogen cycling using isotope geochemistry.
I'm Becky. I'm from the University of Colorado Boulder, and I'm studying photochemistry and using air-water interfaces to build chemical complexity.
Hi, I am Francis Rivera, and I'm from Puerto Rico, but I'm a grad student at UC Davis, and I'm a planetary geologist, and I study sedimentary systems, in particular ice cover lakes in Antarctica as analogs for Mars. And I also do I'm with the MSL team, so I also do robot stuff with curiosity.
I'm John Harris. I'm at the University of Washington in oceanography and in astrobiology. My background is microbiology, biochemistry, and microbiology is what I do, and work specifically in extreme environments like deep sea volcanoes, etc. And I've had an association with George here for a long time, dealing with origin of life for how many years now? And so
for the original life.
both of us have a real passion for this subject, even though we don't understand it. And I'm also looking for extra resources. So.
Hi, my name is Bjarne Menard. I'm coming from Denmark, the Southwestern University of Denmark in Odense. I'm a professor in chemistry, and I'm interested in amphibious self-assembly, protocell, and RNA chemistry. Obviously, this reason in the origin of life. I've also seen all those guys for a long time. I don't know if it's as far as the origin of life itself, but it seems a very long time.
Yo soy Ray y soy un periodista. Periodista y cultural. Okay, that's thank you everybody. This is just to make a little little introduction of what I will do in the next day. I will say this is the third edition of the school. This is the title of the previous school that we have, we have taught on many things. We have taught on Mars, we have taught several times, we have talked about the extremophiles, about prebiotic chemistry. In fact, 10 years ago was the first edition that was original life appeared in the topics of the school.
Hello. Hi. I'm Miguel Ángel Casimiro from the University of Santander.
I went to Bienvenida.
Sí.
Okay. The introduction of the school.
Yeah. Well, let me talk in English because I know that it's international subject. So I am Miguel Ángel Casimiro. I'm the coordinator of postgraduate studies at the University International Pelayo. I always, I think I only came to say hello, to say welcome everybody to this beautiful place and surrounding. I think there is no so many house like this for family courses, so I think you have a great experience. Anyway, I think our university is focused, and this is school mainly in the region of life. I think it's a topic we stay in the border, in the frontiers of the knowledge, and I think that this is a great opportunity to discuss about this topic. Well, as we begin the summer, I have to apologize because I came from another open ceremony. So welcome to this week. Welcome to the Magdalena. Welcome to the University International Pelayo, and I hope that this week will be really useful for you training period. Thank you so much.
Okay.
Thank you.
Thank you.
You're very welcome.
Okay. Okay, this is the more the history of the school. You know that we have worked in Mars, we have talked about the extremophiles, the solar planet. I say that 10 years ago was the first school where original life was mentioned. I'm not sure in this one of the 2005 or 2006 was John Shostak here, Nick Atol, the number 5, the 9. And I think that this edition, we have had 2 editions before. We talked about the origin of building block flight, where who was starting. Also, that more or less in some way in relation with this. We talked about biosignatures in 2013, and that this is cool that in fact we are talking the original life. This is perhaps at the core of the astrobiology. I think that is good that we have seen, which is the background of everyone, that is the daily life is we need to address the study of original life by many perspectives. I think that is very good that in this school we have people from chemistry, we have people from geology, we have people from atmospheric studies, we have theoretical physics on one side. That is interesting. I think that there's totally multidisciplinary, interdisciplinary, I don't know. That is I think that is the only way to study the original life. Because in fact the original life was a study problem from many years ago. In fact, there are 2,000 years, more or less, the concept was quite simple. Was around the spontaneous generation, the idea that this was more interesting. From the time of the Greeks, they say that all they need is something like ice with a beta heat. That was necessary for life. Also, there are some receipts for creating maize that you know there are spontaneous generation of mice that place in the street the other rodents, perhaps a week, another month there, and just 20 days. After 20 days, you have mice. That is a good result. That's mean more or less what is the concept. Life appears from nothing. Spontaneous generation, that is the concept that was in many years, that in fact until the middle of the 17th century was not the first experiment just to find that this is the hypothesis was not right. That was done by already the make a base. They make a simple experiment with meat in a jar, and they say that they appear life in this jar with open and not closed. They appear some sort of jar. The first concept that try to the mid-19th of the 18th century that we start just to move the idea that the spontaneous generation that try to find that some Luc Leclerc and Comte de Buffon, that he was a naturalist, a found naturalist that makes some ideas, that there are some internal modes that try to organize molecules, that it was not a spontaneous generation. The idea was behind the original life. That's something that different that could be proposed, like I said, that some proto-evolution of that. In fact, was Lamarck, that was a disciple of a student of Buffon, that they start to say that something that there is something more. They say that under the influence of light, certain elements, caloric and electric, enter these little bodies that they mentioned that are miscellaneous matter that was in charge to create the light. This was in some way that spontaneous generation, they are not right, they are something that was a extraneous matter that is miscellaneous, they call miscellaneous, that they say that they're from there. They appear, the light appear with some influence from light, certain element, that this is something that in the future was appear on the studies. But in fact, Charles Darwin in the middle of the 18th century make in a letter to Joseph Dalton Hooker, make just something that it was more close to what we have now in mind. That in some one little pond with all sorts of ammonia, phosphoric salt, light, heat, electric presenting, that a protein was significant for them. That this is something, this is advanced many years, was detected, what that detected in some experiment. For that, they are one of the lecturers, Julie Breton, that is not here, make a paper about the Charles Darwin, the original life, what is the concept of original life in Charles Darwin world. That means that you see that is just at the end of the 20th century, give an idea that this world more close that we have now, that this is different than spontaneous generation, that what usually was not, there are some abiotic creation, abiotic basic for the creation of life. It was in Pasteur, in the middle of the 19th century, that make an experiment just to discard totally, to refuse totally the spontaneous generation. That was thinking before, that make an experiment that is clear, where they can, that the conclusion that the microorganisms were transported through the air, through the growth and the generation from the growth itself. That make an experiment with some deposit that was closed, and when they open the closet, open the depositor, they start to grow some bacteria. That is what's clear that from this point that spontaneous generation was totally refused, and that need to think about that. And only was at the beginning of the 20th century was there two ideas was that was the base of we know what the base of the original life study and we know now. That is heparin, the Russian biochemistry, that say that the life arising from simple molecules in the lifeless hell under much different atmospheric conditions than necessary. That they say that there are abiotic creation of life in a condition that the people would have known what in fact was the basis. And also Urey in the 1952 give this support, this content, we conclude that the spontaneous generation must have occurred on the early hell with an atmospheric consistent mainly of hydrogen, ammonia, methane, and water. That this is, I think that this is the starting point of study original life we know now, we are going to know in this school. Supporting this idea, there are two experiments that in the middle of the last century also that support this idea. One was done by Miller, that make a famous Miller experiment, that in some condition, at some time they got some amino acids, the basic amino acid, that is the monomers, amino acid is the monomers that we are talking this week. And also another experiment from Joan Oroz, that is in Spanish biochemistry, that is working in NASA, and they make the experiment also in NASA in the 1960s. And that with the experiment that obtains some other elements like adenine, that you know that is the base for the basic molecules that we have now in the areas and the cellular activity, like ATP. In fact, what is the view we have now? That if this is more or less the idea of the evolution of the idea of the astrobiology, of how is the evolution of the universe, how is the process that at some moment appears in life, that we have something that is related to the astrophysics, that is the evolution in the stellar medium, the evolution of stellar formation, planet formation, but at some point, that is the formation of the planet, start the evolution of the planet. And as a consequence, the idea we have now, this school that we have presented, is at some moment the evolution of the atmospheric evolution, the geological evolution, the organic evolution, kind of life in a planet. And this is more or less the idea we have now. We are talking about everything. This is a consequence of the evolution, and the consequence of many elements that in some moment that is the consequence of all of that is the appearance of life. In fact, there are two ways to study the original life. One is bottom-up, and the other one is top-down. Bottom-up is that the idea that for monomers that complex molecules, what is evolution, and the other vision is the opposite, the top-down, that you start from complex molecules and try to know what is the minimum condition for life. In some moment, these two approaches should be converged, and we should say that that how is evolution of simple elements to complex, and what is the minimum complexity that we need for life. That is the two approaches that in some moments should be converged. And in this moment, I think that we can just pass more to the study origin of life. That in any case, I said that this is interdisciplinary way to study. We need to a contribution to biochemistry, people, the atmospheric science, just to understand how the evolution of the atmosphere in the planet context, how is the evolution, I say, of the planet itself, how is the evolution of the prebiotic chemistry, how is the evolution of the molecules in the surface of the planet, everything all together in an interdisciplinary way. That this is important, that they are not separate areas that should be studied in a different. They should be contributed all together. That this is quite complex, because interdisciplinary in the concept that that's right in the back. Analyze, synthesize, and harmonize links between disciplines in a coordinated and coordinated world. This is the concept that we need to apply for the study of regional life. It is not only a problem of one discipline, it's a problem all disciplines together, and this is the good that we have in this school. People from many areas, many disciplines, everyone with different point of view. I think in this school, there you are seeing complementary view, or you have in mind. This is quite important. I think. I think for us, it's a really success for the school that there are many people from many disciplines all together in the room. This is the main topic, but I think that they are not. This is only the physics theoretical has room for that. That is good that they will have a physics theory here. That there are some people that this is an example that we have taken from the internet. There are theoretical physics people that also gives ideas about the original life. That this is a formal theoretic that say that in some conditions this is not chemistry. In fact, this is not geology. It's more theoretic. That in some way, in some moment, should be just linked to the other discipline. But in this approach, for instance, that this is only an example. This guy has proposed the idea that this is only a physics problem, and the life appear always that there are some conditions, that is theoretical conditions, but they need some source of light, that there are some heat bath around the molecules, and there are some atoms. And they say that this one condition by itself start to create a more complex condition. That this is quite interesting. I think that this is an example that the interdisciplinary approach that we need for astrobiology, for the original life. That is important. I think that this is my main message for this talk. That the original life is interdisciplinary. We are here just to see different point of view of your approach, and that if you get this different approach, this will be successful school. This is also a list of the talk that we have scheduled for the school. Mainly we have, I think that most of the talk is a bottom-up approach. Only we have one that is top-down, that is the last one from minimal genomes at the last universal common ancestor that is going to be done by Julie Peretot. And also we have a global view that about this study original life that will be given by Carlos Briones, that is here. That should be a talk on Thursday night. They give some global view of the study. And just only to finish, just to pick a small bit about where you are. You are in the university, International University Meadows. That is not all was created in the last century, in 1952. The first course was in 1933. From the beginning, it was focused to summer school. This period for, this period was some period in the Spanish history with quite brilliant intellectual. They tried to open to the international collaboration. That in this school that was for the Spanish Civil War, but we have quite useful talkers, lecturers, like I think that also Einstein was here that's talking about something, so his theories. And this school was stopped during the Spanish Civil War, and that said in 1947 was started again like International University Meadows, that is what the scheme that we have now. You see that you take a brochure of the school that this is a quite open school, a university with courses about many disciplines, not only pure science. They are economic. There are some radio, media communication, everything is in the repertory of courses. And the idea that is give the opportunity that in this wonderful place, just to know what's in the last, what the last areas and what in the essence knowledge. And just only to say that during the school, this is at the representative of the school site, that is a very good, beautiful place. We will try to move to downstairs, another a more bigger room than the one was one better. They think that if you have any question, any problem, talk with me, with Vicky, with Costa that is behind the camera. Just try to help you, and that's all. Thank you.
Questions for Javier?
No, we're not.
Okay, everybody. So I'm Victoria Meadows, or Vicky, and as I said, my history is in astronomy, my background, and so I'm going to talk a little bit about sort of the astronomical context for the origin of life. So I'm going to talk about what we understand about the very, very early times in the solar system, as illuminated actually only over the last few years. And so talking about the composition of terrestrial planets and also how our solar system was probably very dynamic early on as well. And the idea here being just to give you an idea of what was going on prior to the delivery of these building blocks and water to our planet that set the stage for life. So I just start with this little cartoon, which I think is lovely. So this is from XKCD. Basically, you have the astronomer looking through the telescope, and then we as astrobiologists are held back by the fact that we're too nervous to balance on the ladder while holding a microscope. So different ways of looking at things. So, and again, speaking to the interdisciplinarity of the school, astronomers and biologists together. So when we start on the story of our planet, behind every planet there's a star. And so we start with essentially star formation. So somewhere in a molecular cloud, there will be a bit that's a little bit denser and will start collapsing, or maybe buffeted by a supernova explosion, something like that. And so that part of that interstellar, sort of this cloud, will start to collapse. And we come then to this idea of the so-called nebula model of planet formation, which says that essentially you start with this large diffuse cloud, you collapse it down. Again, a nearby supernova to shock the cloud helps. This contracting nebula will heat up, spin faster, and flatten out into a disk. And it is from this disk that the planets form. And so this has long been our theory of planet formation. And in fact, there is abundant observational evidence that this is what happens. And so these are observations taken by the Hubble Space Telescope of these sorts of protoplanetary disks around stars in a star-forming region. The structure is a little bit more complicated, though, than just the disk, and so there are some other images we have. So what you're seeing here is the disk edge on. You see the material in the disk. You see the bright upper level, the bowl of the disk essentially being lit by the star, and you see these collimated jets of material that come out from the star as it contracts down, so to sort of lose material and conserve angular momentum. So this is essentially a solar system, a planetary system being formed in these particular images. So that's sort of the kind of physics of what's going on there, but while that's all happening, we have this idea that there's also chemistry going on as well, and essentially what we're looking at in the solar nebula
is about 98% hydrogen and helium, with 2% of what astronomers call metals. So that's anything heavier than hydrogen or helium. So lithium is a metal, by that reckoning. Sodium is a metal, oxygen is a metal, and so on. Sorry about that, it's just the way we are. But so when I talk about metals, I'll be talking about that, not anything I could wear in a ring or whatever. So planet formation, if you take one thing away from this talk, planet formation happens from solids. Okay, a material has to be solid to be incorporated into the body. So if something is gaseous, it's difficult to incorporate into a terrestrial planet, solid body. So you're looking for solid materials in the disk to make planets out of. So at high temperature, close to the star, only metals and rock can condense out to be solid. Everything else is in gaseous form. And so you would expect that planets that form close to the star will be predominantly made of metals, which is in fact what we see. So we have this thing called the condensation sequence, where we show, at very hot, you only get the metals, and as you move further out in the disk, it gets cooler and cooler, and so you're able to condense out things that would normally be more volatile, more likely to go into the gaseous phase. So as you get, for example, beyond about 150 Kelvin, so when you drop down to temperatures below 150 Kelvin out in the disk, you can form ices, water, methane, and ammonia ices. And that point at which the water can condense down into a solid from its gas phase is called the snow line, essentially, or the ice line or the frost line in our planetary system. So beyond that line, further from the star at cooler temperatures, we can get essentially a very big increase in solids because we have not only the metals and rock, but now the ices are also solid as well at that time. And you would in fact expect giant planets to form just beyond that snow line, and that's where the giant planets are in our system. So that does not mean, of course, that there are no rock and ice beyond the snow line. There's no rock and metal beyond the snow line. There really is. So throughout the entire disk, rocks and what you and I would normally call metals are solid throughout the entire disk, but it's only beyond the snow line that we get these ices forming as well. So that's kind of a sort of static, very calm and serene idea of the condensation sequence. But what is actually going on is probably much more violent and a little bit more complicated. And so this is kind of an image of what may well be going on in the disk at that time. And so the green there is the accretion disk. But those circles are showing that there is a lot of circulation of material in the disk. And in fact, there's new evidence from the Stardust mission, which Don Brownlee PIs at the University of Washington, that in fact a very large fraction of all of the solid material in the disk is actually processed very close to the star early on. So even the solid material, the rock-type material that is found in comets very, very far from the star, has probably been processed very close to the star at some point in its history. And so here in this image, the red is the infalling disk. So material is coming into the disk as the star collapses down, but there is also circulation within the disk that processes the material. So this is a slide I stole from Don from a talk he gave recently, which was very eye-opening. So based on the results from Stardust, he says, we now know that the early solar system destroyed about 99% of the material that was in that original cloud. It was processed at temperatures far higher than rock could survive. And so the early solar system was a very violent place with a lot of this physical chemical processing. The inner solar system, though, very, very close to the star, was not particularly well mixed because the accretion times of the planets, the rate at which the planets formed, was short compared to the time that the nebula could mix the material. And so you would expect inhomogeneity, sort of different clumps of different material for the inner planets. But on the diagram there on the bottom right, you can see that there was this probably very large-scale radial mixing of heated material from close to the star out to the outer regions of the solar system too. So the early solar system had large-scale radial mixing of giant grains, which carried the inner solar system grains out to the edge of the disk. And so there was a lot of this very high-temperature processing. And so he believes that most comet dust was made in the inner solar system at temperatures above 1300 Kelvin and then processed out to the outer regions. So his conclusion is that interstellar chemistry, so that material that the stardust from which we formed, actually had nothing to do with the origin of life, because any of that material would have been broken up and reformed in the nebula. I'm not sure that's strictly true, and at least the raw material gives us the basic senses of elements, the carbon, nitrogen, oxygen, and so on. But to get this idea that in fact it wasn't just sort of this classic condensation sequence, but there was a lot of turbulent mixing and some of it at very high temperature. So, from this disk, we get to planet formation. So I'm going to tell you a story about the solar system and how we think planets in it formed, in particular the terrestrial planet you're standing on right now, and also what might have happened in the early solar system. And when I was learning about these things, again, the solar system was a very benign and placid place where planets formed in their own little orbits, nobody moved anywhere, and it was all very neat and orderly. The image we've gotten of the early solar system in the last few years, though, has shown that there was probably large-scale motion of very big planets, and that it, in fact, isn't quite as benign as it seems. But in the beginning, we start with the formation of a planet starts with dust. And so you start with these solid materials that, again, sort of rock and metal that have condensed out of the nebula. And they move around in the nebula, circulating, and they eventually stick to each other via some force, we're not entirely sure what. As they grow, though, they will decouple from the gas eventually. And the gas in the nebula, normally it would like to go around at the Keplerian velocity, so the velocity of a solid body. But because it's denser and hotter in the center, there's a pressure for the gas to move outward. And so as the gas moves outward, it actually balances, in a sense, the gravitational force that's causing it to orbit. And so the gas orbits at a velocity that's slightly slower than a more solid object would. Okay? And what that does is it produces a headwind in the nebula. So the gas is moving slightly slower. It's about 0.5% slower than, say, a solid body, a rock or a pebble. And so that produces a headwind on those rocks and pebbles within the nebula. And that actually causes them to lose energy and spiral back in towards the star. And so you have this motion with the grains forming and then essentially spiraling inwards. And this, of course, one of the first paradoxes or big problems for planet formation is we know that planets exist, you are standing on one, so obviously the process works, but we couldn't get it to work, we the astronomers, because it turns out that gas drag can be very, very bad. So in this diagram, this is looking at essentially the rate of inward motion on the y-axis, so how fast something is hurtling towards the star, against the radius of the particle on the bottom there. And these other curves are showing essentially the density of the gas disk, so essentially the strength of that headwind on the particle. If you look where the majority of these peak, it's at a radius of about 10 to 100 centimeters, so about 1 meter. And so the maximum velocity towards the star occurs when a particle gets to about 1 meter big. When it's smaller than that, it's kind of moving closer to the gas velocity. When it's larger than that, it really doesn't care about the gas. At 1 meter, though, it's sweeping up pretty much its own mass in gas as it moves around, and so it experiences the largest headwind possible. So how bad is that? Well, it turns out if we look down in this diagram, a 1 meter particle, so I guess it's more of a boulder than a particle, if a 1 meter boulder is orbiting around its star at 1 AU, under this particular gas drag scenario, it will spiral into its star within about 100 years. So can you form a planet in less than 100 years? Because I'm not sure the nebula can. So essentially what we're looking at is the catastrophic loss of all of the material very early on and no planets forming. Obviously this is not the case. So at the moment, one of the biggest problems in planet formation is trying to get past what's called the 1 meter catastrophe. Things grow until they get to 1 meter and then they all disappear into the star. So people are looking at potentially trying to directly collapse the dust down instead of having it accrete by colliding with other bodies, to just have it collapse down all at once into an object that's larger than 1 meter, so it no longer cares about the gas. That could be helped by the formation of vortices, so eddies, whirlpools within the actual nebula itself that could concentrate material down so that it gravitationally collapses under its own weight rapidly. Or it could be that planetesimals really form very, very fast on less than 100-year timescales. We're not really sure about that. So anyway, let's assume we get past that. And then we go into a phase of planet formation called runaway growth. So once we get to about 1 kilometer, planetesimals will start to collide and form these larger planetary embryos that are hundreds of kilometers wide. And this particular process is aided by something called gravitational focusing, which, as in many cases in life, means that the big or the richer get big and richer. So this is called after runaway growth, we get oligarchic growth, meaning the few benefit, okay, the oligarchs, the few. And so the idea of gravitational focusing is if I'm a body that's trying to accrete other bodies, and I'm moving in my orbit and I'm trying to gather other material around me, I can gather that material if I collide directly with it. If a pebble comes in and hits me, I can accrete that material. But if I'm also large enough, I will be able to gravitationally focus. I'll be able to change the orbit of things going around me to bend them towards me so that I will collect more material. And so the effective feeding area or growth area of a larger planetesimal can be significantly larger than the actual physical size of the body. And so this is what helps with runaway growth. And of course, the bigger you get, the bigger your feeding area, and so on. And so here's the idea here. You either directly hit, or if you're large enough, you can either create material that directly hits, or you can change the orbit to move it towards you. And that process is governed by this equation, which you do not have to memorize. But all I want you to have a look at there, so that's delta m, so how rapidly the planet becomes more massive is a function of its own area, pi r squared, plus this ratio of the escape velocity of the object. So I, as a planetesimal, will have an escape velocity, and the more massive I am, the larger that escape velocity has to be. What that means is that's how fast a particle has to be going to not get dragged in by my gravitational force. So the larger I am, the larger a bar that a particle has to be able to get past me and escape. And so essentially these protoplanets grow faster if they're more massive, or if the planetesimals they're trying to catch are moving more slowly. But here's the downside of being big. So these oligarchs, as they grow, these larger particles, which you can see in the diagram here, if they catch an object, well and good, they're growing bigger. But if they don't catch it, they actually accelerate the object in its orbit. So they what we call dynamically excite the particles. So the particles are now moving faster having passed the oligarch than they would have been just on their own because of that gravitational assist. And so essentially these objects get bigger and bigger and bigger and bigger, but they get to a point where suddenly the objects they miss are going faster and faster, and so they cannot catch them. So the process is in essence self-limiting eventually, which is good, because otherwise there'd be just one huge planet sitting in the solar system, right? One guy would win if this process didn't happen. So we have the runaway growth, the big get bigger, and then the oligarchic growth, it kind of slows off because the oligarchs are getting too big for their roots, essentially. They are now accelerating the things around them, and they're having trouble catching them. And so you can see in this sequence here, we start off with the oligarchs, the big guys to the left, and the other little planetesimals they're trying to catch. But as time goes on, you see the oligarchs growing, but you also see the planetesimals on this diagram, their eccentricity is increasing. Eccentricity is on the y-axis, meaning their orbits are being disarrayed, they're being accelerated, and their orbits are changing. And so that's the effect of the bodies. So gravitational focusing ends when the velocity dispersion of the small bodies is larger than the escape velocity of the object trying to capture them. So the growth slows down, and typically systems tend to produce a series of oligarchs, you can see in the bottom panel there, of similar mass, separated by about 10 mutual hill radii. So a hill radius is a characteristic boundary where if you're within the hill radius, you orbit the planet or the planetesimal, what I'm calling an oligarch here. But if you're outside the hill radius, you orbit the star. So within the hill radius, you are primarily under the gravitational effect of the body that's trying to accrete. So at about 10 hill radii, that's the typical sort of feeding zone for these oligarchs. Okay, so if we now move to that's essentially the beginning of the planet formation process. After that, I should add, the oligarchs, they form bodies that are about the size of Mars, about a 10th Earth mass. And then after that, we get to something called late-stage accretion, where these big Mars-sized objects are crashing into each other. In fact, one of them may have crashed into us and helped to form our moon. But these objects crash into each other and eventually form the planets as they are now. But if we look at the source of Earth's water, which is obviously important for the origin of life, during its formation, it's so much hotter than it is now, and so that snow line I was talking about was about somewhere between 3 to 5 AU, probably closer to 3 AU. So Earth couldn't actually accrete water from local material because water would have been a gas interior to 3 AU, and so we couldn't sort of collect it into the solid body of our planet. It's not easily. So where does our water actually come from? And this is a big outstanding question. There's certainly evidence pointing in the direction of asteroidal sources for it. But we've recently gotten some information from comets as well that suggests that the comets might have the right ratio, the D to H ratio that would be consistent with our own Earth's ocean. So I think this question is still an open one, although George, you may have more to say about this. So there's these various ways we could get it. Either be delivered by comets, but prior to recent measurements, the D/H ratio, the ratio of heavy water, essentially to typical light water, didn't seem to be consistent, although again we're getting more cometary measurements that say that it might be consistent now. The asteroid belt, though, does have the right D/H ratio, and so the idea was that maybe water-rich carbonaceous chondrite bodies that helped form the planet and brought the water to us in solid form. And another possibility is a primordial atmosphere where we actually have hydrogen wrapped around us, and potentially that hydrogen can be reacted to leave us with a hydrogen budget that allows us to generate water. So there's three ways, yes.
So even with all that mixing that you showed in the nebula, that can't help bring primordial water stuck in the original material from Earth?
Yes. So what I'm going to talk about is, so that original mixing, we were talking more about the solids, but there's also dynamical mixing as well that should bring water. So when I talk about the water coming from the asteroid belts, that is essentially radial mixing. Yeah. So basically radial mixing. So yes, you've nicely introduced my next slide. So basically, this is where we think the water most likely came from. So this is this idea. Here you see on the bottom, these are all little planetesimals waiting to become a planet. We've got eccentricity on the y-axis, and this distance here is the distance from the star. Red means very little water, yellow means getting some water, and blue means very water rich. And so you can see that in this particular case, the snow line is at about 2.5 AU. So beyond 2.5 AU in this particular diagram, the bodies are blue, they're very water rich. And if we look at planet formation, let's hope I can get this movie to work. Okay, so this is planet formation. So you can see in the inner solar system, closer to the star, you see those red bodies forming. So that's the very early terrestrial planets, but red means they're very water poor. With time, though, at about 5 million years, we will have formed a Jovian planet. And the Jovian planets are believed to help with the radial mixing of material. And so you can see as time progresses, note that the colors of the inner planets are changing. They're changing to more water-rich because material from beyond the snow line is being flung in by our Jovian planet to actually help enrich those bodies. And so we finally end with terrestrial planets that are more water-rich. So that is one scenario. I'll just play that again. If you have a look too, note that the I won't play that again. Note that the planets, when I redo this movie, note that the planets that are closer to the star form much faster than those further out. Does anyone even know why that is?
Denser disk.
Denser disk? Something else about planets close to the star? Moving faster, yes, orbital dynamics. They have more chance to collide because they have shorter orbital periods and faster orbital velocity. That's what's going on there. So there you can see the disk being decided essentially by the Jovian. Stuff beyond the snow line is now being flung in, and you enrich the bodies. So that's kind of the sort of standard model of where we think our water comes from, is this particular mixing. So I'm going to just go through, you don't have to memorize this, but just to give you an idea of sort of characteristic timescales for planet formation, it's actually probably way faster than you think. At least it's way faster than I thought. So grains condense within about 100,000 years, which in geological time is tiny. You get your Moon and Mars-sized embryos forming within about 100,000 to 10 million years at the outset, and late-stage accretion to about 10 million to 100 million years. That's when the Mars-sized bodies are starting to crash into each other. And that is actually a very long period of time. The Jovians have to form, the gas giants like Jupiter and Saturn, we know they have to form within 1 to 10 million years because that's how long the gas survives in the disk. And the Jovians have to form from gas. So unless they can form a core that's large enough to wrap the gas around them in a very short period of time, there will be no gas for them to accrete to form themselves. And so we know that gas giant formation has to be very rapid to race the loss of the gas out of the planetary nebula. And that gas is escaping from the planetary nebula because of the stellar wind from the star. Either the star that's actually the host star for the system, or other stars in the cloud, in the molecular cloud as it's forming. It's not just typically one star, it's lots of them. And if you have one of these OB stars nearby, the super big bright blue ones, they have spectacular winds that can strip not only the gas from their own systems, but a lot of nearby systems as well. And so to race the stellar wind from the parent star and any OB stars in the vicinity, you really have to form giant planets very fast. And so, so the Jovian forms within a few million years typically, and so it can actually affect the late stage of planet formation as that simulation showed. Essentially, once the Jovian forms, it enhances that radial mixing, by radial mixing, moving things from outer to inner or inner to outer. Okay, so the growth of a terrestrial planet kind of goes like this. Basically, you start down here with the dust sticking together. So we've got time on the x-axis, we've got the size of the body on the y-axis. Dust, somehow a miracle happens. We avoid the meter-sized catastrophe, so we have to figure out yet what that is. You then go into runaway growth here, where the big get bigger, all right, until they get so big that they excite the planetesimals around them and they can no longer capture them. You then end up with the planetary embryos, and you end up in this late-stage accretion, which is where relatively large bodies are crashing into each other, which is why we have the step-stair function in the growth. And then finally we end with a late veneer, which is smaller planetesimals. Basically the debris gets swept up and added to the body. And so somewhere around this later phase, this is when water comes to our planet and sets the stage for the origin of life. So now it's your turn. Let's see if you can read. So what happens in step 1? That's right. Okay. Right. In 2? Avoid meter catastrophe. Great. And number 3, what's happening? Runaway growth. What's helping runaway growth? Gravitational focusing. Okay, great. All right. What's happening in step 4? Oligarchic growth. And why is it doing that curve? Why is it slowing in growth? Particles are speeding up. Excellent. Number 5. What are we?
Crashing.
Yeah, things crashing, big things. Okay, so this is late stage accretion, big things. And number 6, we're just sweeping up the debris, basically. Well done. Excellent. And so in steps 5 and 6, that's when water shows up. All right. So you followed all that. Great. So the other thing, of course, is about the forming Jovians. I've mentioned already they have to form pretty quickly. For Jovians, at least just beyond the snow line, they preferentially form there because it's just more solid material, so you can grow a large body much faster before that gas dissipates. However, anything sort of beyond the snow line, significantly beyond the snow line, seems to have time scales for collision and accretion that are much slower than is actually required to gather all that gas before it goes away. And so there seems to be some other process in play as well. And I'm not going to go into the 2 competing theories, but one is core accretion, where you just smash things in and you basically create a little terrestrial planet, or actually a big terrestrial planet, that you then wrap gas around. So if it's a joke that was inside every giant planet, there's a terrestrial planet screaming to get out. But the other mechanism is potentially what's called gravitational collapse, and that's when parts of the disk, again through vortices or whatever, may in fact become denser and just collapse all at once to form a giant planet in one go. And that process is very, very fast.
So is it realistic to deliver the amount of gas that you see in Jovian planets just from like really rich, volatile rich, like asteroid comets?
Yeah, I believe so. So I mean, you're looking at about 70,000 kilometers of gas for Jupiter, for example, and so it's much more efficient. And again, only potentially a terrestrial in the center of, say, 1 Earth masses. Okay, so the Jupiter's core may only be 1 Earth mass, and so there's no way you can generate the 70,000 kilometers gas from that. And they have to actually grab the nebula gas. All right. But we have found, for example, giant planets at 35 AU orbits. We found one from B at 115 AU, so there's no way that core accretion can actually form that planet on that period of time. And so this idea of gravitational instability may in fact be the better mechanism there. And of course, as in all science, there's this, it's core accretion, no, it's gravitational instability, it's core accretion. And in the end, the ultimate answer is that probably both mechanisms work, but in different areas of the disk. So when we grow a giant, I just wanted to put this plot up again just to show you the time scale. The time scale we hope is within about a few million years. And this is essentially, this diagram, I won't stay on it very long, but essentially you start with generating the solids and then you start accreting gases in the second phase to accelerate the growth of the giant. Is planet formation too efficient though? There is a possibility that, have I not got the movie? No, I haven't got the movie. Darn, this is my favorite movie. I'll have to try and show this to you later. This movie actually shows two planets forming but far too close to each other. And when they interact with each other, they eventually, what happens is in all sort of Boolean scenarios, one planet gets kicked out of the solar system. It's typically the smaller one, as is typical. And the larger planet gets flung more towards the inner solar system and ends up on a highly elliptical orbit. So you can end up with Jovians in highly elliptical orbits. What could go wrong with that, right? So we have actually found Jovians on highly elliptical orbits in many of the exoplanet systems that we have now observed. And so this particular process is called planet-planet scattering. It's probably quite common. Luckily, it did not happen in our planetary system. Our Jovian is on a well-behaved circular orbit. But if you have a Jovian on a highly eccentric orbit, apart from the danger to planets in the inner solar system, we've discovered that it actually shuts down radial mixing. So if you have a Jovian on a highly eccentric orbit, or even, in this case, 0.2, an eccentricity of 0.2, which is not that elliptical, these are the planets that form. So remember, red is water poor and blue is water rich. So if you have, on the left-hand column there, your typical eccentricity equals 0, so that's a Jovian on a circular orbit, you can form relatively water-rich planets interior. But if we run the simulations again for an eccentric Jovian, it will tend to actually block that radial mixing of water-rich material from beyond the snow line into the inner solar system. And so an eccentric Jovian can be very bad for water delivery to its planet. Okay, so that's something else to keep in mind. That's not our planetary system. The other thing that we've also discovered, at least in models, that hasn't been verified by our observation, but there's this idea that planets might in fact migrate, Jovian planets. And the reason we know about that, and initially nobody really conceived of this at all. I mean, in our planetary system, our Jovians beyond the snow line, that's where we expected to form. We pretty much expected to have stayed there. We didn't imagine the Jovians would come in. And yet the first exoplanets that were found, of course, were hot Jupiters, planets very, very close to the parent star that had clearly formed beyond the snow line, because there's no way they could have gotten a big enough core in time and kept their gas, and then migrated inwards. Okay, so people have run simulations looking at what would happen if a Jovian migrated inwards to the terrestrial planets. We all thought it would be absolutely catastrophic, but it turns out it isn't. As the Jovian moves inward, it actually entrains water-rich material behind it and brings that into the planetary system. So this is a time sequence starting with our Jovian out in the nether regions there. You can see the red. It's not very bright, but the red at the top is the water poor. You can see the Jovian sitting in the water-rich area. It brings in water-rich material, that blue material, and can in fact form water-rich terrestrials both in front of its path and behind its path. So a migrating Jovian may not be the worst thing if it goes in. Let's see if I can get this movie to work. So yeah, so this is the Jovian migrating in. Obviously, it's exciting the planetesimals quite a bit. They're increasing in eccentricity, but you end up with water-rich material inner and water-rich material out. Okay, so let's go back to our adorable solar system, which we believe is so quiet and so well behaved and just a lovely place for the origin of life. Migration didn't happen in our solar system, right? Or did it? Okay, so I'm going to talk to you about a theory. I'm not so sure it's controversial, but it's certainly pretty radical. So a long time ago in a solar system amazingly nearby, your one, this is a model of what might have happened in our early solar system. It was put forward by Kevin Walsh and colleagues in 2011, so just a few years ago. And the idea here is that Jupiter and Saturn may well have migrated into about 1.5 AU in our planetary system and then migrated back out again. Now the reason this model, and this is a model that's not, observationally verified, nobody was there taking photos, but the reason they put forward this model is that it explains a lot of previously inexplicable things about our solar system. And the two things that it explains is, one, Mars is tiny. You may not think anything about that, but it annoyed dynamicists for decades because they couldn't generate a small Mars given sort of a uniform distribution of material in the disk. Mars should always have been bigger in the simulations, so nobody could generate a small Mars. The second thing was the actual distribution of material in our asteroid belt. We have pretty dry S-type asteroids interior and pretty wet C-type asteroids behind. But when they first posited this, they thought, well, this is crazy. If Jupiter migrates in and then migrates back out again, the asteroid belt should be destroyed. There should be nothing left, right? So they thought, well, we'll go ahead and we'll do the dynamical models for this. And again, it's just Newton's dynamics. It's not too difficult to do, but here's the idea. So they call this thing the grand tack. So in sailing, you know, when you sail sort of into the wind and do right-hand turn and go back out again, this is the idea. So what they think is that Jupiter formed and started to migrate inwards by interactions with the disk, the gas disk. Saturn took its time to form, but formed more slowly, and it also migrated in. Because it was smaller, it migrated in at a faster rate. It caught up with Jupiter, as Jupiter got to about 1.5 AU, and the combined interaction between Jupiter and Saturn and the gas disk was enough to actually drag the planets back out. So this was a mechanism that had been proposed prior to this theory, that if you have the two gas giants, they can essentially interact with the gas disk such that they can go back out again. So this is the idea. Orbital distance is on the y-axis, so how far we are from the star. The lower one is the path of Jupiter, heading in towards the star, down to 1.5 AU there as a function of time, and then coming back out again. So this is the main idea. And so what would have happened is Jupiter and Saturn and our planetesimals, as these two migrated in, they would have, of course, caused a great deal of disruption in the disk. And what they would have done is essentially truncated, cut down the planet-forming disk for terrestrial planets to have only material available to form terrestrial planets out to about 1 AU, your current position right now. And so this is the whole reason for this mechanism. To bring Jupiter in, it flings everything out and just truncates the planet-forming disk at 1 AU. And then it and Saturn exit stage left, they go back out again. And so essentially what you're left with once they go back out is a smaller planet-forming disk to generate planets. And you've also, in fact, mixed water-rich material in such that you leave it at the outer edge of the asteroid belt, just like we see it, and you have the dry material closer in. And so this sort of carved triangular shape here is essentially what was trapped within the asteroid belt and kept. The rest of the material is now forming terrestrial planets. And so you end up with essentially a bunch of oligarchs forming in this little truncated disk. See that little red, the distribution of the red is very short. And if you do that, you can actually generate a small Mars. But the point being that there's this tail of water-rich material that was brought in by the Jovian migration sequence. And in this particular model, it's believed that that material was what eventually delivered water to the forming Earth. So this grand tack theory. So it's pretty breathtaking to think that our Jovians would have come all the way in. But because we had two, luckily two, one would have kept going, but two, we can actually reverse the process and go back out again. So if you do this process, you can actually form this. These are their simulations here. You can see they have a bunch of points in various simulations that actually hover around actual Mars. And so they're able to generate a Mars-sized object using this particular scenario. And this is just sort of a top-down view of what would actually be happening. It goes by pretty fast. But I think the point here is, and you'll see Jupiter and Saturn, there they go, Jupiter and Saturn go in, and come back out again, and the net result is this truncated little donut in the middle from which the terrestrial planets form, and you see that it has water-rich material in it as well. And then the dashed line is essentially the asteroid belt that's forming behind. But the exciting thing is it explains Mars, it explains the structure of the asteroid belt, and the entire process does not destroy the asteroid belt, so it is still feasible. It's still something that could have happened in the system. So that's interesting. And finally, I'll finish off here. After that process happens, after Jupiter and Saturn come in and head back out again, and park themselves out there, there's another model which some of you may have heard of. It's older than this particular picture. And it's called the Nice model. So it's generated in Nice. And in this particular scenario, Jupiter and Saturn go back out, but they're still in a disk of planetesimals, things flying around everywhere. And those planetesimals, when they interact, for example, with Uranus and Neptune in the outer planetary system, that interaction, again, like the oligarchs, if you accelerate that particle, you lose a little energy. And so what happens is that the planetesimal interaction with Uranus and Neptune tends to fling the planetesimals in towards the inner solar system. Saturn does the same thing. Jupiter takes that planetesimal and it has enough energy to actually fling it out of the planetary system. What happens overall is that Jupiter moves a little bit in towards the star, but the other planets move a little bit out. And so Jupiter, Saturn, Uranus, and Neptune all kind of do a little, sort of just each time they fling a planetesimal and play kind of catch with these things, they start to migrate very slowly from their position. So this is planetesimal scattering. But eventually, Jupiter and Saturn hit orbits where they're now in resonance, which means that, in this case it was a 2-to-1 resonance, it means for every one orbital period that Jupiter goes around, every one orbital period that Saturn goes around, Jupiter goes around too. And because of that, it means they line up in their orbits pretty much every single time, and so they can have a much larger gravitational effect on each other. And in the end, they destabilize each other. They cause each other to form highly eccentric orbits. This is not a good thing when Jupiter and Saturn go eccentric. And so this essentially disrupts this disk of planetesimal material and causes a large-scale disruption of the orbits of Uranus and Neptune as well. And this flings a whole bunch of material into the inner solar system. And this is believed to be the origin of the late heavy bombardment of 3.7 billion years ago. So I'm going to show this movie and finish up. But this is the Nice model idea. And by the way, Neptune is the blue one here, so it's actually interior to Uranus in this current model. But watch where it actually ends up. So Jupiter is red, Saturn is white. We're evolving. Look at about 600 to 800 million years, things start to get interesting. So Jupiter, Saturn, and then Neptune and Uranus, and not in the right order, and that's the Kuiper belt, the green belt beyond. Okay, so they're scattering planetesimals, and their orbits are changing just very, very slightly until Jupiter and Saturn hit this 2-to-1 resonance. And then all hell breaks loose. Starting to stabilize. Alright. So at that point, notice Neptune's down on the outside. The blue ring went from the second one into the outer one, and the Kuiper belt is just, everything is just dispersed. And so that may well be the dynamical scenario under which we get a late heavy bombardment, which may have frustrated the origin of life or helped it, I don't know, but either way. So that is the story of our solar system and planet formation and water delivery. So the takeaway points are, although the young solar system was formed from interstellar material, the estimates, at least from stardust, is about 99% of that material was destroyed by a processing close to the star. So we got the raw building blocks, but the actual structures of things were destroyed and reformed. Terrestrial planets form within the first 10 million years of planetary system evolution. And their water inventories can be strongly affected by the Jovian, whether it's there, whether it's circular. The solar system may have undergone 2 major migratory episodes, this idea of the grand tack, moving Jupiter back in and out. Again, they just came up with that to truncate the disk so they could make a small Mars, and yet the whole thing kind of hangs together and explains, in fact, the asteroid belt structure as well. And then this idea of the Nice model, the destabilization of Jupiter and Saturn, which eventually led to the late heavy bombardment. And so whether a planet is able to provide conditions to support the origin of life is a strong function of the planetary system architecture and the history of that planetary system. And so we should keep that in mind when we look for life elsewhere in our universe. Okay, so I'll finish there.
I wonder if it's possible to assume that since Earth has lots of water, the inner planets, Mars in particular, also by this model have more or less the same amount of water to start with. Is it possible to assume?
That's the idea of sort of the even water abundance. That was an early idea. I'm not sure it's still widely held, and the reason for that is this late accretion process. It can be quite random. You could get hit with a very water-rich body or not. And in fact, the simulations have shown, like if you run the same simulation 10 different times, you can end up with a water-rich Earth or a completely dry Earth. It's really just a very random process. And so the randomness comes into it, and also the point that Don made about the planet formation happening faster than, in fact, the radial mixing in the inner planetary system, meaning that the material that planets form from can be very heterogeneous, very uneven. And so it's not necessarily clear that everybody gets the same chance at accreting material. The other thing, too, is that the Earth is actually spectacularly water poor compared with a lot of the raw building material, the carbonaceous chondrites, in the outer asteroid belt. And so we actually have a pretty small water abundance. What's it? 0.03 or 0.3% is tiny.
Yeah, 200 parts per million.
300 parts per million.
We're undersaturated with respect to water in a big way.
So we are actually a very water poor body, but obviously enough. not completely water poor. We got enough of the delivery of water to actually make oceans possible.
Is the Mars planetary embryo?
Yeah, well, Mars, it's planetary embryo size. Right, so it just depends on what it accreted in its position.
Like, I remember people came out this year last year and said Mars was really early on.
I know that, do you know who the buttons of Mars? Is it less or more, or we don't know?
We don't really know. We think it lost a lot of water. There's isotopic reasons to assume that it did, but...
Yeah. So that's the other thing, too, is Mars is so small, it just doesn't hang on to volatiles for very long either. So it's lost a lot.
Can you explain a little bit more? I was kind of confused because you said at some point it seems like the solar system should have a lot of these Mars-sized bodies that are kind of slamming into each other. And so why is it a problem that you have a Mars-sized body where it's in our solar system? It seems to be intuitive with a zeroth order that if you already have a bunch of these bodies, you maybe get one of them.
Maybe you get one of them. Yeah, the simulations did not show that. Every time they ran them to completion, they generated bodies larger. And I suspect it's because you were so close. I don't really know, some other dynamicist, but in a wild speculation, I'm guessing because they're much closer to the snow line, there should be a lot more solid material for planet formation and around that area. So the snow line would have been about 2.7 AU is what I've seen in a bunch of them. If Mars is at 2 AU, it's pretty close to that material. So I don't know, but for whatever reason, they had difficulty creating a small Mars. It just wouldn't consistently come up with small Mars. So they used a very old idea of Weatherall's, in fact, because Weatherall said, hey, if the planet forming disk was actually truncated at 1 AU, then forming small Mars is really easy. So that's what they wanted to do. But yeah, you're right, at some level, maybe just a planetary embryo is fine as Mars size.
Do you mind going back to that slide with the hot Jupiter coming in Jovian inner migration? That drags a lot of little water-rich terrestrial planet in front of it.
Oh, the migration of the Jovian inwards?
Yeah, I was just curious because we've been observing a lot of hot Jupiters in these exoplanet bodies. So I'm just wondering if we have all these water-rich planets forming really closely. Your Jovians at only 0.5 AU, and all your tiny little water-rich worlds are extremely close to the host star. Are any of these, would any of them end up in a habitable zone? What's the evolution of the volatiles in those small planets?
Right, so most of the hot Jupiters that we've actually found are even closer than that. They're like at 0.05 AU, 0.03 AU. And the interesting thing is that we have found that hot Jupiters are lonely. So we have looked for other planets in the systems with hot Jupiters.
Right, but could that be an observational bias? We're just not seeing those tiny little ones.
So that's the other thing. If there are very much smaller things there, potentially we are not detecting them because they would be further out and beyond the Jovian. The hot Jupiters we're finding tend to be very close. So yeah, I'm not sure we have the observational capability yet to find these things. But
I'm just thinking theoretically, like what happened to these little guys?
The other thing too is that this just forms them. It doesn't stop them from spiraling to the star. Right. So that's the other. There could be further evolution beyond this actual formation scenario. But I would say that based on what we know, we typically see the Jovians in further. There are some out here as well, though. Jovians have been found along this entire range, but there tends to be kind of a peak of them near what's called the 0.0. So 3-day or 0.03 AU pile up. So we see the Jovians, they come in and they stop in that position. So there could be nothing interior to them anyway when they get to there. This one is stopped fairly farther out in the simulation, so maybe there's something in of it. But I do not know of any systems like this where we've actually found a terrestrial interior to the Jovian. But it should be possible because when they're close to the star, they're relatively easy to detect. So I don't know. I'll look into that and see if we've actually found an evidence-ready system like this. But at least this showed this is at least possible they could form, but it doesn't say what happens to them afterwards.
That's exciting.
It's at least it's not catastrophic. We thought it would just fling everything out and it would be hopeless. But I think we're more likely to find the water-rich bodies that form afterwards, after the this material up here, they didn't run the simulation through, but that could eventually form another planet, say, at 2 AU.
I was wondering, in all these models, what's the probability to have two terrestrial planets almost with the same size? Why do you think Venus and Earth have almost the same size?
I think it's not unlikely, and again, it just depends on how many of in the late stage accretion, how many embryos crash together. I think in the Grand TAC, the model, of course, they published, showed something that looked very much like a solar system. They were able to get almost evenly sized. They had a small Mercury and Venus and Mars. Venus and Earth and Mars. And so I have certainly, there's nothing that precludes that. Nobody talks about the Venus problem, but the Mars problem is always famous. So.
Maybe because they are very close to each other, maybe there's a connection.
Yeah, they're pretty close. I mean, they have a connection dynamically. They speak to each other, Venus and Mars. We're almost in synodic resonance, essentially, with Venus. But I think it's just in-planet formation, the luck of the draw, how much material comes in, but it's not unreasonable to form two Earth-sized planets. I mean, as you know, too, we're finding systems where we have super-Earths, but many, many times larger than the Earth. We don't have one of those in our planetary system for whatever reason. So a bigger question is, why did we not form a super-Earth? Everybody else seems to have one. Why do we not have, a planet significantly larger than the Earth in our planetary system? Any other questions? One more question.
Just curious, how many other models are able to give like a super Earth scenario or something that would give something that would be like an Earth-like planet? I mean,
in the models?
I mean, like how many other models out there that can say, oh, you can get like an Earth-like planet? I don't know.
Yeah, no, they can form. Actually, I had another slide that I took out, but yeah, if you run all these simulations, you can generate Earth-like planets with Earth-like water abundance and size fairly regularly. As long as you keep your Jovian, in Jupiter's position 5 AU in a circular orbit, it's relatively straightforward to form Jovian with these terrestrial with these dynamic models. So it's not that rare.
Okay, make some break.
Make a break. Okay, we'll do
Go on.
12.
Okay, go ahead.
So,
in the downstairs.
Oh, downstairs. Okay, downstairs at noon. And yeah, we can go back up to the Palacio and they have a little cafe bar where you can buy coffee and snacks and things like that.
You can go to the palace and also to the Caballerita.
Oh, the Caballerita.
That is the other vision you have seen from the end of this.
So the stables down here also have a cafe in them.